Welcome back to eCoreAcademy, everyone. My name is Anita and I am a teacher and co-founder here at eCoreAcademy. As you can see, I'm bringing to you all a new Biology 1 episode, and this is going to be on ionic and covalent bonding. So in the past few videos, we've looked at atoms, molecules, bonding, etc. And the reason we're doing this mini unit on chemistry is because this is pretty much biochemistry. It's not just chemistry, it's biochemistry. And the reason it's biochemistry is because it's going to be essential for us when we look at macromolecules, which are coming up very soon, especially when we analyze the ways which the main elements of life, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, how they interact, how they make bonds, and etc. to make molecules and, to build up to macromolecules and then make us. So that is why we're looking at chemistry-related topics, and today we're going to specifically focus on two types of bonding, ionic and covalent, and we're also going to talk a little bit about metallic bonding. So the main reason that atoms bond are to attain a stable configuration. So in this video, we're going to be asking ourselves the question, why do atoms bond us, and why do they want to attain this stable configuration? And in order to attain that stable configuration, how do they bond? What are the types of bonds? How do these atoms interact? What constitutes a bond? How are bonds formed, etc.? So we're going to be answering those questions in this brief video. Again, this is not meant to be a super in-depth chemistry video because you can just, when we eventually make a chemistry course at eCoreAcademy, we'll devote probably a whole unit to learning about how electrons play a major role in bonding and how atoms bond. But this is really just supposed to be a quick little thing to go over key vocabulary such as ionic and covalent bonding. So when I bring that up, when we talk about macromolecules, you're not totally left in the dark about what those words, what these phrases, what these scientific words mean. So before I get into the lesson, I would really appreciate it if you all could like the video, subscribe to the channel, hit the post notification bell, drop a comment down below, and share it using our socials. Okay, so let's get right into the first slide. So the first question we're going to ask ourselves are, why do atoms form these bonds? Despite the bond, it doesn't matter if it's ionic, covalent, or metallic, just a general question, why are atoms forming these bonds? So let's go back to a concept I introduced in the last video, which was the octet rule. So octet means 8. Octo, or that word kind of has that root of 8. So whenever you hear anything started with octo, octet, that means 8. So the octet rule. So this has to do with an 8, like an 8 count of something. So what this means is atoms strive to complete their outer shells with 8 electrons to become stable like the noble gases. As you all know in the last video, atoms have a nucleus, and then around that nucleus they have shells. So each shell is like an energy level, and each energy level has sub-levels. So the one closest to the nucleus would be energy level 1, and then as you move outward, you're just adding 1. That's called a quantum number. So each energy level has its own quantum number. The outermost energy level, and the amount of energy levels per atom will differ depending on the periodic table, but no matter what that outermost energy level, atoms are always trying to complete that outermost energy level with 8 electrons. There are always exceptions to this rule, but for now, for our purposes, because we're just looking at an overview of chemistry, atoms are trying to get 8 electrons in their outermost shell, and the outermost shell is known as the valence shell. The reason they want to do this is because by filling that outer shell, they become stable. Meaning it's like, if you want to think of it this way, they're saturated. You can't add any more, and you don't really need to take any more off. So they're in almost like an equilibrium, like a perfect state. They don't really need to undergo any more chemical reactions because it's almost like their goal is attained. So they become stable. They don't need to react, so they become inert like the noble gases. The noble gases is that last group on the periodic table. They all have full outer shells with 8 electrons, except helium. Helium is the exception. It has 2 valence electrons, but that's because it only has 1 shell. So that's the exception. But all the other noble gases have 8 electrons in their outermost shells, and that's what the octet rule is pretty much saying, that all atoms want to achieve that. So a good example, I know I use oxygen a lot, but oxygen has 2 electrons to fill its inner shell. So oxygen has a nucleus with 8 protons and 8 neutrons, and then it has one shell outside of that nucleus, and the innermost shell can hold a maximum of 2 electrons. So the innermost shell of oxygen is filled. It has 2 electrons. It has a second shell after that, and its second shell has 6 electrons. And if you want to look at a neutral atom of oxygen, if it has 8 protons, it must have 8 electrons. So if it has 2 electrons in the inner shell, then it has 6 electrons in the outer shell. However, because the outermost shell wants to reach that octet rule, wants that 8 electrons, oxygen is looking for those 2 more electrons to fill its outer shell. So in order to do this, in order to fill its outer shell, it's not like oxygen is going to go drift off into space and just grab random electrons. Instead, it's going to form bonds with other atoms that can give those electrons to it. In this case, it's going to share those electrons. So to fill its outer shell with 8 electrons, oxygen may share electrons with either a single carbon atom or 2 hydrogen atoms. And these are just 2 examples. There are many, many other instances of ways oxygen can bond. But here, if you see the 2 hydrogen atoms, hydrogen has 1 proton per atom. So if oxygen bonds with 2 hydrogen atoms, those 2 hydrogen atoms together will provide 2 electrons, filling oxygen's outer shell. If you look at carbon, carbon has 4 electrons. So if you look, it's actually depicted in the diagram here. The circles represent electrons of oxygen. So like here, this would be an electron of oxygen, this would be an electron of oxygen, and then the X's represent electrons of carbon. So these two would be electrons of carbon. If you see this overlap, these are the electrons that they're sharing. So oxygen has 4 of its own electrons, but it also is sharing these 2 electrons with carbon, and carbon has its own 2 electrons here, but it's sharing 4 electrons with oxygen. So by sharing their electrons, oxygen now has 8 electrons in its outer shell. 1, 2, 3, 4, 5, 6, 7, 8. Carbon, which originally had 4 electrons, now that it's sharing 4 more electrons with oxygen, it has 8 electrons in its outermost shell. So now they both are stable, and they're stable by bonding. So that's why atoms bond, to reach that total of 8 valence electrons. So let's talk about the 3 main types of bonds now that we understand why atoms bond. So first of all, what are chemical bonds? So generally put, they're attractions between atoms, specifically the valence electrons of atoms. So you're going to put it simply, when 2 atoms are attracted to one another because of reasons such as trying to fill their outer shell, etc., that attraction is what constitutes a chemical bond, and that attraction is specifically caused by the valence electrons of atoms. So remember, the valence shell is the outermost shell of an atom, and the electrons that are found in that shell are the valence electrons. And valence electrons are responsible for many bonding properties and characteristics of atoms. So, for example, in that last example, oxygen has 6 valence electrons, and those 6 valence electrons are very close to a complete octet, complete outer shell. They just need 2 more electrons. So those 6 electrons are almost like pushing the oxygen atom, hey, look for another atom that can give you 2 more electrons, then we'll be totally stable. So they almost encourage the atom to fill its outer shell with 8 electrons. So the 3 main types of bonds that atoms can form. So this is what most of this video is going to be about. The first type is covalent bonds. Covalent bonds are where electrons are being shared, like in that last example. It's where you have 2 atoms and neither of them has a full shell of electrons. What they do is they share the electrons with one another so that in the end, each of them has 8 electrons. So in that last example, oxygen had 6 valence electrons, and carbon has 4 valence electrons. By sharing, carbon shared 2 of its valence electrons with oxygen to give oxygen a complete shell of 8, and then oxygen shared 6 valence electrons with 4 more valence electrons with carbon to give it a full shell of 8. So that's an example of a covalent bond. Ionic bonds are where electrons are being transferred. So I'll go over an example of this, but this is where you have 2 atoms, and what happens on the periodic table is on the left side of the periodic table, you have atoms such as lithium, and you'll learn more about this in chemistry, but you have atoms like lithium that want to give up their electrons, because what happens is in their outer shells, they only have maybe 1 or 2 or 3 electrons. So to get so what they'll do is, instead of trying to gain another 7 more electrons or another 6 more electrons or another 5 more electrons to fill that shell, they're like, it's so much easier if I just get rid of these electrons. So they shed that outer shell that just has 1 electron. The secondmost shell has a complete set of 8 electrons. So it's almost like, if you think of it this way, the second, like, if this is the outermost shell and it only has 1 electron, the shell that's right inside of it has a full 8 electrons. If this atom just gets rid of that 1 electron on the outside, this shell that had 8 electrons that was inside the outermost shell, it becomes the outermost shell, and then the atom becomes stable. I know it's a bit complicated to explain, and you'll understand it when you do chemistry, but that's just the whole concept. Just understand that some atoms, instead of wanting to gain all the way to 8 electrons, they're willing to lose, and by losing, they can actually get down to 8 electrons. So ionic bonds are formed when some atoms that want to give up these electrons give electrons to atoms that want those 8 electrons, those electrons to become an octet in their outermost shell. And then that's how an ionic bond forms. Lastly, metallic bonds. Metallic bonds are found in metals where electrons are also shared. So they're very similar to covalent bonds, but they happen in metals, and we'll talk about them later because they're a bit different. So I'll hold that to the end of the video. And here you see 2 diagrams. Here's an example of ionic bonding. Here we have an atom that wants to give up its electron. So what it does is it transfers its electron to this atom, which really, really wants that electron, so that it can fill its shell and get 8 in the outermost shell. And when that electron is completely transferred, so it's completely given away from this atom to this atom, you have a transfer, this atom up here has lost 1 electron. And it originally started out electrically neutral, meaning it had an equal number of protons and electrons. If it got rid of an electron, it has 1 more proton than neutron. So now it's overall positive. It has a +1 charge. This atom down here was originally neutral, but it gained an electron. So it has 1 more electron than protons, and it has a -1 charge. So this is a positive ion, which is called a cation. This is a negative ion, which is called an anion. Here we have covalent bonding. This is a bit different because if you see, both of these atoms have electrons, but instead of transferring the electron, they share them. So here you can see that overlap. They're sharing them. One atom does not take the electrons, and one atom does not just give the electrons. They're sharing them. On the next slide, we'll talk more about how this sharing can be a bit unequal, as in maybe this atom up here hogs the electron more. But compared to an ionic bond, this is where the atoms are actually sharing them. They're not completely giving up atoms, and they're not just completely they're not completely giving up electrons, and they're not completely taking electrons. Okay, so now let's talk about covalent bonds. Covalent bonds are electrons are being shared. Like we saw, there's that overlap. Electrons are not being fully given away or taken, they're just being shared. So there are types of covalent bonds. There are 2, and I'll briefly go over them. There are nonpolar covalent bonds, and all you need to know about these are that the electrons are shared equally, such as methane. A good example is methane, which is CH4, which you can see down here. So this is a nonpolar covalent bond. So in the middle, you see the carbon atom, and around it, you see 4 hydrogen atoms. So carbon has 4 electrons in its outermost shell. Each hydrogen atom has 1 electron in its outermost shell. So hydrogens want to fill their shell by getting 2 electrons. Carbon wants to fill its shell by getting 8 electrons. So what they do is they end up sharing. If each hydrogen shares an electron with the carbon, then the carbon's going to have a total of its original 4 electrons plus 4 more electrons. It's going to get 8 electrons. If each hydrogen is sharing 1 carbon atom with the carbon, then each hydrogen is going to get 2 electrons. So there's an equal sharing. Everyone is happy. So everything is shared equally. However, you have it says polar bonds. It should say polar covalent bonds. So polar covalent bonds occur when electrons are shared unequally, such as water, which is H2O. So you see this oxygen here, and you see the 2 hydrogens. And you see these signs. These mean partial positive, and these mean partial negative. Because what happens is the electrons spend more time around the oxygen than the hydrogens. So oxygen has 6 electrons. Hydrogens have 1 electron each. Oxygen wants 8, hydrogens want 2. So what happens is these hydrogens will bond to the oxygen, and so it's going to share electrons, but the electrons are going to spend most of their time around this end of the oxygen, just because it's almost like oxygen dominates. So oxygen has 2 more electrons just over here, and it doesn't really want to sorry, not two. It has more electrons over here, so that's why this end is more negatively charged. So just know that in these situations, it's electrons are not equally charged. If we come over here, I'll just quickly go over this. This is O2, so an oxygen bond to oxygen. Oftentimes, you'll find you'll find elements such as oxygen, nitrogen, hydrogen. These gases, they in nature they don't occur just as one. So you won't just find one oxygen atom. Usually, they bond in pairs. Think of it like a couple. They like to bond together. So often you'll find O2, and probably most of you are common with dioxide. So that's why you see two oxygen atoms, but when they're bonded together, they are equally sharing electrons. So that's why this is a nonpolar covalent bond. So whenever you see covalent bonds, if you write them out, sometimes you'll see them represented by a line drawn between atoms. For example, H, and then you see the line H. This is supposed to represent two hydrogen atoms bonded together, which is H2. You could write that as O, that little dash O, which would be two oxygens bonded together, which is O2. And just keep in mind that covalent bonds are more common amongst nonmetals. So nonmetals are found on the right side of the periodic table after that like big block in the middle of transitional metals. You'll find them on the right side. So what happens is nonmetals will bond together to form molecules, and you'll talk more about that in chemistry. Just keep that in the back of your mind. So let's continue covalent bonds. So in covalent bonds form, both atoms have a complete outer shell of 8 electrons, like we talked about. Atoms bond so that they can obtain that octet, so that it can obtain those 8 electrons in the outer shell to become stable. In the instance of covalent bonds, this is done through sharing electrons. So you can achieve this. You can achieve the octet by single bonds. You can do it through double bonds or even triple bonds. I'm not going to get into too much detail about that, but just know that with covalent bonds, you can have single, double, or even triple bonds. Single bonds, you'll just see that one dash. Double bonds, 2. Triple bonds, 3. The triple bonds are pretty rare, but you might run into them. So just know what they are. A good example of this is a water molecule. I always bring up water because water is a really big part of this unit. We'll actually be doing a few lessons on just the chemical properties of water because it's so unique. So in a water molecule, each hydrogen atom is sharing 2 electrons with an oxygen atom. So as you can see here, these two positive, you see these plus signs, so those are just protons because hydrogen atoms are pretty much just a proton and an electron. They don't even have neutrons. So these are the two hydrogen atoms, and they are sharing, each of them are sharing 2 electrons with the oxygen, but the oxygen is hogging its own 2 electrons up here, its own 2 up here, and then in its inner shell it has another 2. So that's why they're saying weakly positive. So a partial positive charge here and a partial negative charge. Because as you can see, it's not like the methane molecule where the electrons were equally shared. The oxygen is almost keeping those 4 electrons to itself. It's not letting the hydrogens touch those 4 electrons. Whereas the carbon atom was letting each of the hydrogens touch any of its electrons. So it was sharing all of its electrons. In this case, oxygen is only sharing 2 of its electrons. So it's keeping the other 4 to itself. Here's just 2 other models. This is called a 3-dimensional model of a water molecule. So it's like a space filling model. So these are just different ways. This is a ball and stick model, I believe. So these are just other ways of depicting oxygen. Let's talk about ionic bonds. So ionic bonds are where electrons are being transferred. So they're not being shared necessarily. One atom is giving an electron up, and another atom is accepting that electron. So electrons are being entirely transferred. So think of it this way. You and your sibling, when you're little, your parents bought you both a toy. Covalent bond would be where both of you are forced to share that toy. And a nonpolar covalent bond would be where you equally share that toy, so you both spend an equal amount of time with that toy. A polar covalent bond would be where maybe you use the toy for most of the time, or your sibling uses the toy for most of the time. Ionic bonds are where it's as though your parent bought the toy, but it's only intended for one of you. You're not meant to share the toy. So maybe your parent bought the toy and it was meant for you, or your parent bought the toy and it was meant for your sibling. So it was only meant for one of you. So if you want to think of it that way, I don't know, I just came up with that off the top of my head, but that would be an example of an ionic bond. So ions are what are formed after ionic bonds occur. So ions are just what happened to atoms. So atoms become ions after they form ionic bonds. So these are electrically charged particles that form after a transfer. And there are two types of ions. So remember, before ionic bonds occur, ions are actually atoms, and atoms are electrically neutral, meaning they have an equal amount of protons and neutrons. But because one atom is going to end up giving up an electron and another is accepting an electron, that balance is messed up. So the net charge is not zero anymore. So what happens is the atom that gives up that electron has one more proton than it has an electron. So it has a net positive charge, or +1. So it's a positive ion that has given up electrons, also known as a cation. The atom that accepts that one electron, well, now it has one more electron than it has a proton. So it has a net negative charge, or -1. So it's a negative ion that has gained electrons, also known as an anion. Ionic bonds occur between a metal and a nonmetal. Just keep that in mind. So you might have a nonmetal from the right side of the periodic table bonded to a metal on the left side of the periodic table, more on the left side in the middle of the periodic table. So ionic bonds will always occur between those two. For example, the best example is NaCl, sodium chloride. So sodium is a metal, chlorine is a nonmetal. They bond together and they form salt. So that's an example of an ionic bond forming between a metal and a nonmetal. So let's continue with ionic bonds. And I'm going to talk about sodium chloride. So in the diagram below, in this one here, an ionic bond has formed between a negative and positive ion, making the compound NaCl. So in this case, sodium is the positive ion, Cl, chlorine, is the negative ion, and they have bonded through an ionic bond, and they make the compound. So they bond together, and they make the compound NaCl, which is sodium chloride, which is table salt. So the sodium, which is your Na, it ends up losing an electron from the outer energy level, and it's now a cation with a positive net charge. So in this ionic bond, this up here is your sodium, this blue one, and as you can see, it's giving up one of its, as you can see, this outer shell, it has only one electron. And if you see the second most shell, this shell right here that my laser is on, it has 8 electrons. So if it gives up that one electron, its outermost shell will become this one right here, and that shell has 8 electrons. So it's almost like it's shedding that outer shell, and then its secondmost shell, which has 8 electrons, becoming its outer shell and makes it stable. So what it does is it wants to lose that one electron, gives it up to chlorine, and now its outer shell becomes this one with the 8 electrons. Now it is a cation because it has more protons than electrons because it gave up an electron. It has a positive net charge. And the opposite's true for chlorine. So chlorine, as you can see, its outermost shell has 7 electrons. There's one missing right here. This makes it very unstable. It really, really wants to react. It's almost like you're right there at the finish line, but you're not quite there yet. So it really wants that last electron in its outermost energy level. So it's going to accept that electron from sodium, and then its outer shell is going to be 8 electrons. But because it gained an electron, it's going to become negatively charged with a negative net charge because it has one more electron than proton. So it becomes a cation. I'm sorry, an anion. Cations are positive, anions are negative. Okay, and lastly, let's talk about metallic bonds. So metallic bonds are obviously found in metals. Metals are found on the left side of the periodic table and towards the middle. Electrons are being shared equally in metallic bonds between metals, and they give metals properties such as malleability, conductivity, luster. Like for example, their shininess, their ductility, just all those properties that you find in metal. That's why metallic bonds are very special. And I just really briefly want to go over this because really we're going to be looking at covalent and ionic bonds for macromolecules, but it's important you understand these two. For example, like we said, they give metals those special properties that metals have. If you see here, you have two atoms of zinc, and they have a 2+ charge, meaning they lost 2 electrons. So now you can even look at them as cations. So what happens are metals typically want to lose their electrons. So if you put a bunch of metals together in a space, what they're going to do is they're just going to release their electrons, whatever electrons were in their outer shell. They're just going to release them. And they're called delocalized electrons. So these are pretty much just going to be electrons just floating around in this if you want to imagine an enormous space full of zinc zinc atoms, and they just lose their electrons. They're called delocalized electrons. They kind of just float around. So that's pretty much, in short, that's how metals will form metallic bonds. The last thing I do want to talk about is electronegativity. So electronegativity is how much atoms want electrons. So a great example would be NaCl. So sodium, as we saw, it really wanted to get rid of that one electron. So it was like, let's just get rid of, someone take this electron. I don't want it anymore, because when I lose that one electron, my outermost shell becomes my second outer shell, if that makes sense. Like we said, it sheds and then it becomes those 8 electrons on the outside. So it really wants to get rid of that electron. But chlorine, on the other hand, has 7 electrons. It's so close. It wants that one last electron. So sodium really wants to get rid of its electrons. Chlorine really wants to gain an electron. So electronegativity is a measure of how much a specific atom wants to gain electrons. So the more an atom wants electrons, the higher electronegativity. So in that case, chlorine would have a much higher electronegativity than sodium, because chlorine really, really wants that last electron, whereas sodium wants to give it up. So just like I said here, chlorine is highly electronegative. Chlorine is highly electronegative negative because it has 7 valence electrons and wants one more to fill its outer shell. Lithium, on the other hand, just like sodium, it has 1 valence electron and would rather give it up. So its second to last shell, which is complete, is the outer shell. Like we said, if it has 1 electron on the outermost shell, does it really want to do all that work of gaining 7 more electrons to fill that shell, when it could just get rid of that 1 electron, and the second to last shell, which is already complete, could become the outer shell and make it stable? So that's how these atoms will work. And here are just some measures for those of you who are interested. So if you measure the electronegativity of these atoms, and if you actually measure the electronegativity of their bonds, you can determine what kind of bond has formed between atoms. So if atoms have a net electronegativity of 0 to 0.5, it's a nonpolar covalent bond. So a complete equal sharing of electrons. The electronegativity is 0.5 to 1.7. It's a bit more electronegative, because what happens is one of those atoms is trying to pull the electrons towards itself, so it's an unequal sharing of electrons. And then electronegativity over 1.7 is ionic, because in an ionic bond, think of it this way: one atom's just like, I'm not compromising, I'm not sharing any electrons with you. You have to give me all those electrons. So an ionic bond is where one atom just completely takes the electron, or electrons in that case. So think of it this way: the lower it is, the more the atoms are like, yeah, we'll share with each other. Then in the middle, they're like, yes, we'll share, but I'll take a little bit more. And then the most is, no, I'm not sharing with you at all. I'm going to take the electrons. So that's just a rundown of electronegativity. And again, you'll be looking at this. This is actually a periodic trend. You'll be looking at this in more depth in chemistry. So that's all I have for you today. I hope you enjoyed the video, and please look out for more Biology 1 videos. We'll be wrapping up chemistry, I think, with this video, and we'll be going right into water. So look out for water. Water is so interesting. I can't wait to talk to you all about it. Please like the video, subscribe to the channel, hit the post notification bell, drop a comment down below, and share using our socials. Check out our website and reach out to us at our Gmail if you'd like to. Again, I hope you enjoyed the video, and see you next time. Bye.